Ready to go. Hi, everybody. My name is Andy Mills. I'm a senior research fellow at Sheffield University in the Department of Automatic Control. And our research group is what's called a UTC, a University Technology Centre, supported by Rolls-Royce. So we do the majority of our work for Rolls-Royce in the aviation sector. And one of the big themes in aviation and across industry, I think, has been adoption of digital twins. So I wanted to provide a bit of an insight here as to what that means for aviation. From a personal perspective, not particularly from a Rolls-Royce company, university perspective. Also, then go on to talking about what we've learned from a recent application in a slightly different environment to what I know some of the researchers here are looking at, where you're taking very heterogeneous sets of data, very open environments, not much control over that data. In theory, we have an application of health monitoring of gas turbines where we should be getting back data that is well known, well understood. But I think I'll try and explain some of the challenges that even then we have been facing. And before I embark on that, I just wanted to touch upon maybe some of the interfaces that aviation might have with DAFNI. Up to date, we've been independent from the initiative, and I just thought it got me thinking as to what the interface might be with some of the activity that's been going on. Obviously, there is a transport leg to the DAFNI work. So there is all the current airspace and airport infrastructure that could relate to the existing models. But I think that there's a real opportunity as we look a bit further forward into disruption that's going to happen in aviation over the next few decades, where we're going to see increased amounts of urban air mobility. So this is air taxis idea. How is that going to change the landscape? We're modeling traffic before. What's it going to mean when we try and model aircraft? Small personal aircraft systems. Grid infrastructure. I think that could potentially fall under electrical grid infrastructure could fall under the DAFNI remit. As electrification takes place in aviation, there has been cited lots of opportunity for using what are going to have to be very large batteries on aircrafts, stored all in centralized locations, potentially around airports. That will give demand on the grid, but it will also provide an opportunity to the grid to use that electrical storage for stabilizing the grid. And so I think there are, the list goes on. There are lots of opportunities for expanding what we're talking about today into the widest possible sense of aviation, and going beyond what we're talking about. So probably food for thought for another time. So I will move on to what we're doing now. So I think Daniel earlier touched upon this. Industry, and particularly marketing departments with industry, love calling any modelling digital twins now. Anything they can show snazzy graphics for, they will call a digital twin, and that's nice for bringing in shareholders to the table, I think, but probably not great for doing what the engineers want to do, which is really using models for replacing very expensive development programs. And none of this is new. Using models in place of real life tests has been around certainly since I've been doing my career, and I'm sure before as well. I remember when working on a Eurofighter Typhoon project back in 2004, the big thing was the certification of lightning strike simulation. So they didn't have to take an aircraft and put it through a very expensive verification program to ensure that it was safe under potential lightning strikes. And that was all the way back in 2004. Modelling has evolved, but what probably we are on the cusp of is doing better with models plus data, which is really what I think has been emphasized today. You know, we want to, in aviation, have either as-built models or as-operated models. The first being when we manufacture let's take a gas turbine, you know, hundreds, thousands of components, very high value, some of these components, and they need to be integrated into a whole system. Often they're reused and repaired. There are individual tolerances. And today, an example is that the assembly teams choose from a big bin which turbine blades to put onto an engine in a particular order to try and you know, balance out a mix of the really good ones and the slightly less new blades. You know, being able to do that in a virtual way would enable you to select the best components for a particular engine that fit together ideally, and understand how those as-built components will actually manufacture in the real world. So it would help us model individual deterioration mechanisms of a particular engine number. And then we have the sort of what I'm calling as-operated models. So this is tracking the performance of an engine as it goes through its life. So what is it actually exposed to in the real world? We design components to be incredibly robust against worst case scenarios. You know, we use the same engine that's got to take off in Dubai at 50-degree heat as we use in much more benign environments. So are there design modifications we can do and specialize those components if we knew better what the conditions were, and use that also to make better predictions of what the asset is doing. So that's usage. The performance of the engine. I'm going to talk about this in a bit more detail later on, but we want to know when things are starting to go wrong, pick out incipient signs of wear and tear. Today we do that on a fleet basis, and we don't know we don't have a good understanding of the individual engine and how it is behaving exactly. There's this term going around called the biological age of a machine. So this is the same way that a person can be, you know, relatively fit and healthy, or a bit more in need of attention. The same thing applies for machines. You know, you have very good ones that never cause any trouble, and some which are less good. And being able to track those and understand how good and bad those machines are is incredibly important, and can be enacted by having models of that system, but also they need to be updated as we collect data from them. And then finally, the actual operations of the asset. You know, if we could model that entire infrastructure of exactly where the planes are today, so we've probably got a good model of that at the moment, then can we understand what's going on inside maintenance depots at all times? Can we feed all that together to do better airspace management and actually start to make decisions on that airspace management in real time based on models? So clearly there are hierarchies of scale in the models that we want, both at a fleet level and a component level, in order to be able to achieve this. Okay, so here's my picture of what goes on today. So remote asset management, as I say, a gas turbine example, applicable to lots of machines that are remotely operating around the world, be it trains, truck fleets, whatever. This particular example, Rolls-Royce have got about 13,000 engines in operation on lots of different aircraft types, flying around, sending very limited data due to technology limits back to ground. And we want to use that data through data trending and analysis to inform how different airline operators, of which there can be, you know, about 800 of these operators, should use different depots and schedule in their maintenance repairs, understand what they should do, economically optimize the fleet. We're not talking here about safety. The safety is baked into the aircraft. This doesn't require a digital twin to achieve that. We're trying to understand the asset performance. So what I've tried to illustrate, hopefully you can see my cursor, is a imagined kind of fault that we might see in an engine. And we might expect to see much less pronounced than this, but very small amounts of deterioration that occur on gas turbines because they are operated at such extreme temperatures. There's a drive to make them so lightweight, they need the high performance. So we might expect the asset to deteriorate over time. So this is going upwards against increasing decreasing the asset performance, and that occurs because the mechanical properties of that system, which are very difficult to observe because they're inside an engine, are changing. So what we typically do is we model what normal should look like. You know, we expect some normal degradation, but we want to be able to trend that over time. So we get data back. We determine what data best models this true asset performance of our nominal engine, and we set some alerts against that. So we say if this data feature that we're collecting from our data that we get back, if it goes above a particular level, we send some advice. If it goes beyond this red limit, then actually we're starting to enter problematic areas where the mechanical properties of this system are questionable. And that's the ideal scenario. There's lots of scatter in that data, lots of scatter in the fleet. So we set these thresholds to be able to balance detection and false alerts. But then, of course, we get a real asset which doesn't quite behave as maybe we expect. It's slightly out of family. That's this dotted blue line. So its true performance is a bit different, not drastically, nothing serious going on here, but the data it produces, because the data features that we get are designed from the nominal behavior, are way out from what the true behavior is. And in order to mitigate that problem, we have to do lots of inspections. We have to put a boroscope down the engine, look to see what status it is. And that data is used from the boroscopes to determine whether we should keep operating this engine or whether we should remove it. And eventually, if things, you know, if we can't understand what's going on, often it's removed. And because of that, we remove it way too early, way before it hits this red threshold line. So we lose a load of value from what we could get out of this engine, and we lose a load of asset performance that could have been useful. And as we're going through this process, because the data coming back is giving us lots of false indications, we're getting a massive amount of disruption. So all of those things, you know, it's a real burden to handle all this data. And we want to do a much better job of using models with that data to calculate the true asset performance, to really be able to determine what the mechanical properties are of the system. I infer that from a physics or a data-driven model, and incorporate all that into the asset management and start making adjustments to the system to make it perform better. So really closing the loop on getting data back and actually updating and controlling it. So in order to do all of that, we're going to need to have an ability to get that data back. And we're doing that over often legacy infrastructure. Sometimes there is available cellular data links, satellite links, very expensive really to use on the aircraft. And even when they're there, airlines are loath to use those links for engineering data when they could be charging the customer sitting in his seat money to stream videos, etc. So there's always an economic driver to make to send back as little data as possible. And we potentially have gigabytes of data, terabytes of data generated by hundreds of sensors streaming at tens, hundreds kilohertz of data for vibration and the like, streaming back. We can't possibly send all of that back. So what we do here is we have a concept of using a novelty detection scheme based upon a onboard digital twin to determine what is the most important data. We don't care if we can model that data well, because that means we already know how the asset is behaving. We want to know what's unusual. And we prioritize that data, running algorithms on board the engine, and send back short snippets of data back to ground, which we triage and try to use the off-board fleet data that we've collected to assess over the entirety of the engines that are operating. Is it truly novel? Did we send back novel data? Did we just send back stuff that we were uncertain about? And we use that to update our model, send back a parameter set. And we've got to do all this under a set of challenges. Many of those are around the accuracy of the simulation. We've got to be very accurate over all possible operating regimes, all transients that the engine does through takeoff, through descent, all the different phases over different types of environments. We have lots of variability within the different asset classes. We have only got a certain amount of onboard processing capability on our engine that we can use, and we're subject to also lots of commercial constraints over security and various regulations, and all of that has got to be trusted. So verifying that this system is absolutely key, and that's probably what we spent most of the time doing. What we've come up with is a solution which uses deep models to capture the very complex behaviour of the engine. We did this after trying to evaluate simple solutions first, and found that deep models were really the way to go. Training those based upon all the data that we're getting across the fleet initially, and then specialising those models to work for a particular asset is the preferred way we want to do that for various reasons, and then selecting the right data to make sure those models are up to date in an active learning type scheme. And we've taken this conceptual cartoon idea and actually implemented that on real hardware on a real engine, which is pending flight testing at the moment. So we have a convolutional neural network running on our engine, taking data in, making predictions for a particular parameter, and looking at the residuals between those predictions and what we're actually seeing. When we see something unusual that we think is worth capturing, we acquire that data at very high frequency, and we send that data back to ground, where we use the entirety of the fleet data to allow us to do better characterization of that data that we sent back, and then update the labels that we gave that data. And based on those updated labels, we can update the model and send a new set of weights up to our network. And these networks incredibly efficient using computationally efficient using this TensorFlow Lite toolbox. We're now able to run hundreds of models for different parameters and different combinations of inputs to give us diagnostic coverage over the engine. So we can pick out novelty in any signal that the engine is producing, and use that to trigger our data acquisition. So we've got a really rich set of data that we can then move forward with, and actually use for all of those things that I talked about in the start, for building our model of how the engine is truly operated in the field. The key thing I wanted to bring out is these real world constraints that I think we are in the process of overcoming for aviation, to allow us to start building these rich digital twins. We can call it lots of different things, active learning, but I quite like thinking about it as a closed loop on data acquisition, and basing the data you acquire based on the needs of the system. And we're currently taking that forward to be more mature in its technology, TRL6, getting it ready for putting into a real engine project, and we're going to be flying on some flight tests on an engine very similar to the one here on a business jet in the very near future. That's kind of really exciting for us to be actually flying around the world, hopefully in the future on all aircraft with our models. And none of that had been possible without the team, particularly people who've worked on this project are Adam Hartwell, Felipe Montana, and Will Jacobs. And they've done a fantastic job, all of them, at getting towards a solution that has been approved to test further. And no definitive papers to go and read yet, but watch this space. We have 2 papers in preparation that will cover both the through life learning process of our digital twins, and also the embedded models that have been also integral to detecting the novelty and getting the right data back to our models. So yeah, I hope that was some kind of whistle-stop insight into what we've been doing in aviation, and maybe just a flavour of what we might do in the future.